Thank you so much, Kareem. Thank you to everyone that's here. I see a lot of people I know, a lot of good friends, and I appreciate your support. I also want to say a huge thank you to Kareem and Angel and Indrani Harrison and the whole RI Meetup team for inviting me here. It really is an honor to be a presenter for you today. So I'm assuming everyone can see my screen. So I'm going to be talking to you today about artificially intelligent computer vision. So this is a little bit about myself. There's a picture of me on the right next to the Space Shuttle Endeavour, which is right across the campus from USC. I just graduated in December with a Master of Science in Astronautical Engineering from the University of Southern California, and I'm a proud URI alumni from in the Mechanical Engineering department. And I, right now, am an adjunct professor of physics at Roger Williams University. So my background lies in internships at Raytheon and Lockheed Martin, and I also worked as a student faculty member in the URI AI lab, and then I moved on to, at USC, I was working in the USC Rocket Propulsion Lab. So I just want to preface this with saying, I don't have a formal education in computer science. A lot of the background that I gained in computer science was actually through URI's AI lab. So if you aren't specifically studying something, then that's okay. You can always teach it to yourself and be successful, I think. Here's a presentation overview. First, I'm going to give a brief introduction to what is AI and what is deep learning in the context of computer vision for some of you who may be new to this concept. And then I'm going to really dive into a case study, which is going to be fastener detection using deep learning computer vision. This was what my research was all about. After I go through that, we'll have a session of questions where you can ask me anything you want. Let's start off by talking about artificially intelligent computer vision. So in today's world, we have a lot of different tasks, such as defect detection, drone inspection, and self-driving cars that are vision-based tasks. If you're unfamiliar with defect detection, I remember reading an article about detecting the defects in railroad spikes. And imagine that's something that's a visual task that you really want to automate because you have thousands of miles of railroad. And if one of those railroad spikes has a defect in it, that could cause problems. So that's one application, and drone inspection is where you fly a drone around and take pictures of like a power plant or a facility to make sure everything is in spec. And we're all familiar with Tesla's self-driving car feature. And you can see the picture on the bottom where we have bounding boxes and labels on different objects in the image. These require a computer to use a camera to do what's called computer vision, which is where we take input data and use math in order to make a determination on what we see or what the computer sees. There's classical computer vision techniques, which looks at individual pixels and looks at curvature and assigns values using hard-coded elements. That's has its own benefits and limitations, but for the tasks I described just a second ago, AI is a more fitting method. So let's talk about AI. AI, and more specifically deep learning, is something that is it started really in like the 1950s. I won't go too much into it, but the picture on the right sort of gives you a graphical approach of that deep learning is a subset of machine learning that's a subset of artificial intelligence. And deep learning is a type of computational method where we're using something called a deep neural network, which is a math model that's organized in a structure that's loosely inspired by the human brain in terms of how neurons are connected. Deep neural networks require training from a lot of data that you have to take manually or automatically. There's different ways. Overall, it just takes input data, it processes it through an error correcting function to minimize its mistakes, and then comes up with an output prediction as to what it's trying to solve. So the performance of a deep neural network is greatly determined by the training data and the parameters that are provided by the practitioner. The practitioner being me, or another artificial intelligence researcher who has to go in and turn the different knobs in order to make a deep neural network do what you want it to do. Because if you don't do that, you're going to get something that programmers usually refer to as garbage in, garbage out. You don't give it something that's helpful, you're not going to get something useful out of it. So at a high level, the picture on the right is like a graphical representation of how you can think of a deep neural network. On the left, we have the input layer where we take raw data and then it passes it through the deep neural network, which has multiple hidden layers. And then it produces an output in the output layer as to its prediction. So the hidden layers are just sets of functions that detect features in the input data. And based on those features, a prediction is generated. There's different types of ways that a deep neural network can learn. The specific way that my research focused on was called supervised learning, where you give a deep neural network a bunch of data that you amassed and then annotated and gave it to it so that it could train on. So an analogy I like to think of is that a deep neural network learns sort of similar how you might use flashcards to study for a test. It takes an unlabeled piece of data, which is like the front of the flashcard, the term that you're trying to study, and it makes a prediction as to what's on the back of the flashcard. Okay, what does this term mean? All right, so let's do that with a stack of flashcards. And that stack of flashcards is going to be your batch size, or mini batch size is something that we're going to talk about later. Basically, you'll go through the stack of flashcards, make the predictions as to what's behind it, and then at the end of looking at those flashcards, you'll turn them all around and see which ones you got right and which ones you got wrong. And the deep neural network at first makes seemingly random predictions, but through a lot of iteration, it's able to determine the pathways that it took when it got the answer correct. And it'll reinforce those pathways and make those pathways stronger so that the next time it looks at a batch of data, it's a little bit more accurate. So if you spend more time training, it becomes more accurate. But there's actually a tipping point called overfitting that we'll talk about later, where if the deep neural network trains for too long, it basically just memorizes its entire training data set and it can no longer generalize to new data. That's a problem. But in general, more training results in a better deep neural network to a point. So hopefully that gave you a bit of a high-level understanding of AI and deep learning specifically. Deep learning is really just machine learning with more hidden layers. So just a more beefy mathematical algorithm in comparison. And not to get on too much of a tangent, but deep learning was really, is only something that's been around for a very small amount of time because it was only made possible through the advent of GPUs, graphical processing units, in order to process a lot of data at once. And GPUs were actually developed because of video games. People wanted to run higher fidelity video games, higher definition at faster frame rates, and GPUs were good for that. So video games are kind of, you know, helpful in terms of progressing deep learning. So these pictures on this slide show you what to expect in the context of what I'll be talking about today. On the left, you'll get an input image, something like a raw data of just pictures, so pixel values. That raw image is processed into the deep neural network, which is kind of a black box. It's just a bunch of math functions. And then at the end, it'll come out with detections. So your final product is a picture with boxes that surround the object you're trying to identify with a title. So that classification and localization is something that I refer to as detection. So detection will just be used to denote classification plus localization. Let's talk about my research. This is going to be a case study on fastener detection using deep learning computer vision. On the right is sort of a teaser for what the research is all about. It's detecting cross-recessed screws, which you're all familiar with. They're screwed into everything. You know, lots of devices have these. So what are some problems that benefit from having some sort of deep learning computer vision system that detects fasteners? It seems like a very specific thing, but there's actually two main problems that the research is trying to address. And the first problem is satellite servicing, actually. So let's talk about that. Orbital debris is an ever-growing problem. We're rapidly increasing the amount of satellites that we're sending into orbit, and a lot of them, you know, we don't really have strict regulations on how to deal with derelict satellites. So, I mean, there's some stats here that the amount of orbital debris reached 3 million kilograms in 2013, and it's only rising. We'll talk a little bit more about the technical aspect of that in the next slide, but our existing mitigation methods aren't globally practical, because it's not just the US that is sending stuff into space. It's India, it's China, it's Russia, it's so many different places. And NASA can't just come up with some sort of rule that everyone's going to follow. It doesn't really work that way. So nominally, satellites use propulsion for orbital station keeping, because in low Earth orbit, there is still an appreciable amount of drag, atmospheric drag. Although the atmosphere is rarefied, there's not a lot of particles, it's still enough to eventually deorbit something. But retired satellites no longer have the capability, or usually they just run out of fuel in order to keep themselves on orbit. And it actually gets worse farther out into orbit, because they don't even have drag to naturally deorbit them. So our current suggestion is, NASA suggests that, not enforces, but just suggests that retired satellites either lower their orbits and re-enter into Earth's atmosphere, or raise to a graveyard orbit. But it takes a lot of fuel to do that. It's there's a lot of technical challenges. The more fuel you have, the much more expensive it's going to be. And usually investors aren't so keen on giving you a lot of money based on, oh, we want to, you know, add this much more mass to our spaceship just so that it can deorbit at the end. People are usually only, you know, focused on, let's get the job done, and then whatever happens after that, we're not going to worry about it. But that's becoming a problem. Robotic servicing can reduce the need for more satellites by extending the life of current ones. If we go up there and repurpose old satellites, there's a possibility that to reduce the need to send more. Also, sending humans on repair satellite missions is extremely dangerous and costly. So we want to try and avoid that by using robots, and computer vision can be used to aid robotic servicing missions in the detection of those features, such as fasteners. So a closer look at orbital debris. In the space industry, we like to work in kilometers per second. Sorry for those who use miles per hour, but to gauge this, a bullet usually travels around 0.8 kilometers per second. And to get to low Earth orbit, once you're there, you're going 10 times the speed of a bullet. Imagine the damage a tiny shrapnel piece would incur on another satellite. On the bottom right, you can see like orbital planes. If you have two satellites or satellite constellations in the same radius orbit, but different inclinations, they pass through each other's plane twice in orbit. And you can have multiple orbits a day. So there's a lot of chances for collisions to happen. And on the top right, you can see a block of aluminum that was demonstrated to show the damage that would be imparted to a thick block of aluminum by just a tiny piece of shrapnel going at such high velocities. So it's dangerous. So let's talk about the low Earth orbit situation. Getting to LEO costs a lot less than getting to any other orbital destination, so it's popular. There's a lot of satellites going there. And the thing is, because it's low Earth orbit, all of the satellites have a narrower swath width, which the picture in the middle right shows what swath width means. It's just basically the area of satellite coverage. The closer you get to Earth, the less you can see. So it's incentivized to send constellations of satellites up into that orbit just to maintain the same coverage as something that would be a satellite farther out. So now we have a ton of satellites up there in LEO because it's cheap to get it up there. And two, now we need constellations to get the same coverage. Now, the good thing is satellites in LEO will eventually burn up because of the natural drag, but the bad thing is there's going to be a lot of retired satellites that are constantly changing their orbits due to the drag. Now, beyond LEO and into GEO, which is when your orbit is co-rotating with Earth's equator or angular velocity, you're still going super fast. And there's no drag really. So the satellites have no way to naturally go away. They're just going to keep accumulating. So if we want to send more satellites into space, we need to deal with this problem. And of course, anti-satellite weapons make the problem that much worse. Now, here's another problem that is helped by fastener detection: electronic waste processing. It's another rapidly growing problem. We have millions of metric tons generated every year, and it's only growing. And the stuff that we do recycle, we're sending to developing countries to process, and those developing countries don't have health and safety regulations that are properly enforced. So they're leaching the plastic off of these items and in order to get the precious metals that are inside of them. And that's releasing all these toxins, they're burning it. And it's like, who knows if they even have proper footwear. It's dangerous. So we need an automated, non-destructive disassembly method for recycling e-waste. So let's use robots. They offer a potential solution that effectively takes humans out of the loop. The problem is it's hard. Automated disassembly is a harder task than automated assembly. You've probably seen assembly lines with those giant orange robot arms that put cars together. That's still extremely challenging. However, in assembly, you know the positions of all those components. You don't have to figure them out. In automated disassembly, unless you're disassembling something that you created, you're not going to know where all of those fasteners are, and you aren't going to be able to effectively take it apart. So a robot, in order to automatically take something apart, it must obtain the position and classification of those components and fasteners by making a visual observation of it using a camera. Then once it takes that image or video, it has to process it using some type of math to obtain the position and the type of fastener to great accuracy. And the robot must interact with it in order to take it apart in a non-destructive manner. Now, this is really hard to solve unless you have AI, because AI is able to adapt to situations that are unpredictable, being that when there's different lighting conditions, there's different camera angles, distances, imperfections, and other unknowns that you really can't control in an automated disassembly process. So fastener detection is a common approach to these two different problems. Robotics creates the ability to remove the risk to humans. Computer vision is required for vision-based tasks, and deep learning makes that computer vision generalizable to unpredictable environments. So the research that I helped conduct focused on training an AI model to detect specifically cross-recessed screws. And this research has now been published and is freely available through the link at the bottom of this slide. That's a picture of me on the left, Dr. DiFilippo in the middle, and Dr. Jouaneh on the right. And our work is titled Deep Learning Computer Vision for Robotic Disassembly and Servicing Applications. So here's a bit of an overview on our approach of how we tackled this problem. Because we really just wanted to prove to ourselves and prove that this was a viable means to detect fasteners. So here's how we went about it. First, we chose to investigate a feature that's commonly involved in a lot of disassembly processes. So the feature that we chose is cross-recessed screws. The pictures on the top right are some pictures of cross-recessed screws. As you're all familiar, they're in tons of devices. So we figured it would be easiest to focus on that because we can create our own data set fairly easily, compared to like Torx screws are harder to find. Then we found the best deep learning computer vision system at the time to use for that application. And then because this is a very specific problem and no one else on Earth had published, to my knowledge at the time, no one had published a data set of cross-recessed screws that I could just use. So I actually had to manually collect and annotate that entire data set of electronics with embedded cross-recessed screws. So there was no choice other than to create that data set myself. And if you didn't know, URI actually has an electronic waste processing center at the bottom of campus, which is where, thank you to them for letting me take a ton of pictures of all of the electronic waste that they process. So I went to a whole bunch of different places to amass this data set. And then we developed a systematic training model to optimize the DLCV system, DLCV just standing for Deep Learning Computer Vision. And then I'll talk about the testing results, conclusion, and then the ongoing work. So that's sort of how the rest of this presentation is going to go, and it's also how we went about this problem. So first we identified the best deep learning object detection system that existed at the time, which is called YOLO. It stands for You Only Look Once. And if you look up on YouTube, there's TED Talks about this. It's a very popular option for object detection. And it's called YOLO, You Only Look Once, because using one deep neural network, it simultaneously predicts the bounding boxes and the object classes in that one deep neural network, which is different from other ones that usually do the localization in one deep neural network and send the classification to a different one, which takes more time. It also achieves probably the highest accuracy in general for a wide range of applications. It's the fastest option, and it's the most popular. It was very important that it was the most popular because that meant there's a lot of documentation online and there's a huge troubleshooting community behind it for me to go to for questions when I inevitably run into problems. So YOLO is a big family of different object detection systems. The specific one we chose is called Tiny YOLO V2. It's a second iteration of YOLO, but a more lightweight version, which enabled me to really increase the input resolution and some of the other hyperparameters that I'll talk about in just a sec. On the right, you can see some of the absolutely like super impressive detection this is able to do based on a data set of a ton of different objects. Unfortunately, cross-recessed screws was not one of those objects, so that was my job. Because this is a varied application, it calls for a varied data set. To train this system, I took 900 images of general hardware with embedded cross-recessed screws. Those are the pictures on the top. Just a sample of the pictures. There's actually 900 of these. And the test sets, I did 3 different test sets, 90 images each. And this was to quantify how well my system was producing predictions as to where the screws were. Some important things in case you ever want to use this data set. All the images are unique and they were taken through one camera to be consistent. It's 12.3 megapixel camera in equally diverse lighting and visual environments. And because this was a massive task, I felt like it was my civic duty to make it open source. So if you ever need a fastener detection data set, don't worry, just type in this link on the bottom of this slide and you should be all set. Here are some important factors to take into consideration when I was training my deep neural network. The desired object class I was focusing on was cross-recessed screws. And this is problematic because they're very, very small in relation to an overall image. Obviously, if you take a closer picture, then you're able to have the screw take up more of the screen. But usually you want to take, you want it to still be high resolution and take a picture of a electronic device from afar and locate all of them at once. So really needed high resolution here. Cross-recessed screws come in tons of colors, shapes, and sizes, and they're easily confused with other objects that could be commonly found in electronics, like holes, like grates, and other types of screws can be confusing for classical computer vision methods. AI has the strength of being robust against these different distractions. So the meat of my research was turning the different knobs so that I could adjust to the best performance for my specific application. The 3 knobs that I was really tuning here, the first 2 being the most important, is input resolution, mini batch size, and learning rate. Input resolution is the image resolution that the system scales the input image to for processing through its neural network. So I took all these pictures in 12.3 megapixels. That's 3036 pixels by 4048 pixels. So it's a very high definition picture. But usually, the stock YOLO V2 is running at 416 by 416 pixels. That's not good enough to detect small, little, tiny screws. I had to go in and change that. So higher input resolution means that more information about the screw is preserved, but this is dependent on available GPU resources, which is a bit problematic. Mini batch size is a little more complex to describe. Basically, it is the number of images that the deep learning computer vision system trains on before making its adjustment to its neural pathways. it's the number of flashcards that it looks through before looking at the back of them. So a higher mini-batch size means that the model's learning will be more representative of the problem it's trying to solve. Because if it only looks at a few and then makes a huge adjustment to its neural pathways, it's sort of made a huge adjustment in possibly the wrong direction. So you want to have a big input resolution and you want to have a big mini batch size, but you can't because they're both dependent on available GPU resources. They're competing assets. So the third hyperparameter, as they're called, is learning rate. So how large of a change does that deep neural network make to its weights after it reviews each mini batch of images? Well, a large learning rate correlates to a large change after it's looked at a certain amount of data. A small learning rate means it converges at a smaller rate. So thankfully, that one's not dependent on available GPU resources. So the bottom line is I needed to find the optimal compromise between input resolution and mini batch size while utilizing maximum GPU resources and while using a consistent learning rate strategy. This is the method that I came up with. I know it's a lot of text, just bear with me, because this is something that could be applicable to more problems than just the one I was trying to solve. It's a 6-step process, and the first step is identifying the highest input resolution the given GPU can support at the default mini batch size. Then you select several evenly spaced mini batch sizes above and below the default value and find the corresponding input resolution for each one that maxes out the GPU. Next, you have to obtain a training and testing data set of images with a resolution equal to or greater than the highest input resolution that was determined. You want to do this because if you start with lower resolution images, you can't upscale that and create more information. You always want to start with more information and then narrow it down from there. Fourth, you want to train one model at a time at each input resolution mini batch configuration using the consistent method that I'll talk about in just a minute. Then you evaluate the performance of each trained model on the test sets and choose the one that operates the best for use in the field. Here are the 7 models that I investigated. The default mini batch size was 16. I decided to investigate a range from half that mini batch size to twice that mini batch size. So as we said before, larger mini batch size means more images for it to train on before making a change to its neural pathways. More is good here. And input resolution is inversely changing to mini batch size because they're competing assets for GPU, as I said before. And theoretically, you want to have the highest input resolution possible so that when you're processing images, you retain as much information about those screws as you can without, any data loss. So 1184 by 1184 is the lowest, and then 2368 is the highest. And for each of these combinations, they all utilize 100% of the GPU. So these are like the maxed out models for the given GPU that I was working with, which was, I was allowed to use that GPU through the URI AI lab. It was an NVIDIA Tesla V100, and it's got 32 gigabytes of RAM. So really, it was a fantastic machine, and I'm very grateful for their support, because if they didn't give me this access, then this research would not have been as successful for sure. Here's the learning rate decay method that I used. As I said, you want to start with a high learning rate, because you're starting you're starting very far from the target you want to achieve. You want to start by taking large steps towards the target, and then once you get closer to the target, take smaller steps. That just is a method that allows you to converge better on a solution. If you just had a high learning rate, you'd sort of bounce back and forth between the optimal target. So that's why each of these start with a high learning rate and then they drop down to a lower learning rate. Each color signifies a different model. So they all look like they converge at different times, but here's where it's consistent. You want to first train a given model at a high learning rate until the minimal prediction error is reached at that learning rate. And then once you reach that minimal error, you then continue training at a lower rate until the minimum error is reached for that rate. And to understand this graph, the x-axis is just steps. So one step is one iteration through a mini batch of training data. So, you know, it took on the order of thousands of times of looking through, you know, up to 32 images at a time before making a change to its neural network. As I said before, earlier in the presentation, too much training can result in overfitting, where the model just basically memorizes its training data set and can't generalize to new data. And secondarily, something to keep in mind was just the sheer time scale and cost of this training. Training each model generates tens of gigabytes of data, and it takes tens of hours to complete. So it's definitely a challenge. So here's some of the data that we gathered based on how it was training. There's a metric called reported loss, and you can think of it as the higher the loss, the less accurate its predictions are. And once it hits this knee of the curve here and starts to flatten out, it's starting to converge closer to an optimal solution where its loss is very low. And this picture on the left is the entire training process for all 7 models. And on the right, it's just a zoomed in version of that point where it starts to converge. Some important things that we realized were that models that process the higher input resolutions, like Model A has the most input resolution and Model G has the least. Those models that had the high input resolutions initialize at higher training losses, and they converge in the order of increasing input resolution, which makes sense because there's likely more information to learn from higher resolution images. A second thing that we realized is the models with lower mini batch sizes evoked more noise in the reported training loss. As you can see, Model A had the least amount of the lowest mini batch size, and it had the most noise in its reported loss. Whereas if you go from here to the left, from A, B, C, D, E, F, G, it gets smoother and smoother to the left. And that makes sense because the lower the mini batch size basically means that the model's updating its weights based on an iteration of training that is not as representative of the problem it's trying to solve. So if you have a higher mini batch size, then the learning is more normalized and you get less reported error in terms of the loss noise. To move on from training, after a model has been trained, you then want to test it. And in order to quantify how well your model is performing, you need some standardized performance metrics. The 2 main metrics I used were average precision and frames per second. Average precision is like an analog for accuracy, but I just want to be more accurate here by going into it a little bit further. It tells you technically it's the area under what's called a monotonically decreasing precision recall curve where precision is the y-axis and recall is the x-axis. And precision and recall are just metrics that have to do with the number of the ratios of true positives and false positives, false negatives and such in the ground truth objects. Basically, if you make an incorrect prediction, then that reduces your average precision. Something that's used to determine a true positive versus a false positive is what's called intersection over union, which is graphically represented in the top right. We have the ground truth object, which is the object that was labeled by a human, being me, telling the computer, okay, you're not going to see this until we test, but this is where the screw actually is. Then the computer is going to make some detection, which is going to have some area of overlap with that actual ground truth location. If the detection has the correct classification and this ratio of the intersection over the total area of the intersection over of the union, which is the combined area of the overlapping detection and ground truth, if that ratio is greater than 50%, that's a correct classification. That's a true positive. A false positive is anything less than half that. And you can change that percentage based on how strict your application is. Frames per second is a little bit more intuitive. It's just how many images are you processing each second. So those are the two performance metrics that I investigated. Here's some examples of detected output images from my best model. Now, this table actually includes all of the incorrect, like it includes a lot of correct classifications, but see, there were 4 false positives that were recorded here, where it mistook some other feature for a screw. This is all of the false positives this model made in the entire 90 image data set. So if you look at some of where it did the right thing, it didn't mistake all of these holes for screws and instead correctly classified where the actual ones were. This also successfully missed the holes and correctly classified the real screws. So there's a lot of positives going on here. And this one even, it just had an intersection over union less than 50%, though it correctly did encompass the object. A notable observation that we found based on our frames per second, which makes sense, is that if you process higher input resolutions, the frames per second consistently goes down. That makes a lot of sense. There's more information to process, therefore it's going to take longer to process that information. That's just something that's helpful to make sure it's consistent between all the test sets so that there's no fluke going on and everything's sort of making sense. You'll see that the order is on the ones of frames per second here. Max is 3 frames per second. You know, traditionally, YOLO runs at 60 frames per second on the right GPU, but that's running at a super, super low input resolution of like 416 by 416 pixels. We're running at much higher definitions here in order to get that fidelity we need in order to distinguish between the different fasteners. So that's just a notable observation. And the conclusion we were able to make by testing all 7 data sets against all 3 test sets was that there was a single combination of mini batch size and input resolution that resulted in the optimal average precision. These 3 plots are just showing basically the A and B show a deconstruction of the of 2 dimensions of this 3-dimensional graph, where input resolution, mini batch size, and average precision are graphed 3-dimensionally. As you can see, there's the one combination of that worked out the best is 16 mini batches, a mini batch size of 16 with an input resolution of 1664 by 1664. So by doing this trade study, we were able to figure out which configuration worked best for our application So that was a pretty big success for this project. And you can see that the average precision is quite high. We're getting in the 90s here, which is really good compared to some other prior research that we were comparing ourselves against. Now, granted, there is not a lot of prior research in fastener detection that specifically uses deep learning models. However, or ones that are even using classical computer vision models. But among the ones we looked at, we sort of outperformed those. So we got upper lower to upper 90 percentile in accuracy while getting the lowest detection time, which is just the inverse of frames per second. So this was a huge success for us, and the project does not stop here. There's ongoing work happening right now, and the two professors I was working with, Dr. DiFilippo and Dr. Jouaneh, are working directly with a graduate student, Austin Clark, whom I've known for a number of years. He's one of the top students here, and he's working on implementing the model that we worked on into a robotic test bed, and then from there, modeling that robotic manipulator for fastener disassembly. And then later on in the project, we'll focus on augmenting that computer vision model for multi-class detection. So looking at more than one type of fastener. Anyway, I also want to acknowledge the URI AI Lab and the NASA Rhode Island Space Grant for making this research possible. Thank you so much for your support. And now I will open it up for questions.